Hi, my name is Jim. The amount of energy necessary to move an electron in a conductor, or for that matter an insulator, has to do with the resistance of the material, how much it resists the movement of an electron, how much energy it takes to move it. And we can define, therefore, the resistance as being the opposition to current flow. And if we look at the formulas here that sit under the hood on this, and let me get rid of this guy right now. If we have this symbol here, it's a Greek rho symbol. That's the characteristic resistivity of the material, say that be aluminum or copper or silver or gold or whatever. And then we see that it's multiplied by the length divided by the area. So the longer a wire is, given a constant area, the more the resistance, and given a constant length, the thicker we make the wire, the larger the cross-sectional area, the lower the resistance. So that's going to lead into explaining some of the American wire code with regard to sizing house wiring, and for that matter any other wiring. So what we can kind of allude to here is that, and rho, by the way, includes other things too, like temperature, how materials act at temperature, resistance, dependency, and so on and so forth. So if we take a look at a pipe here, is what we see is that the area of this here for a large and small pipe is obviously this can carry more water than this can over a given distance. Now, when we talk about wires in cross-sectional area, it's a little bit different than the area of a circle in that it's not pi. So the area in cm, that circular mils, is simply equal to the diameter squared of the actual wire. So in areas you have to not confuse that of wire cross-sectional areas with the cross-sectional area of, say, a circle, because it's a different formula, a lot easier to work with. So if we take a look at resistance from another standpoint, and suppose we have a pipe here and I have an input pressure, inlet pressure of 40 psi, and that's kind of typical. We have a well here and the range is from 30 to 50, and depending upon the length and size of the pipe, I may only get 36 psi out of the pipe. So what that amounts to is a pressure drop of 4 pounds per square inch in the pipe, and this is relative to the atmospheric pressure. So what I can say there is that the 4 psi has to do with the resistance of the pipe, and that assumes, by the way, that we do have water flow through the pipe. Statically, if we had no water here, like a garden hose, and the nozzle were turned off, the pressure at both ends would be the same because there would be no pressure drop in the pipe. And we're going to see the equivalent of this in electrics later. So if the pipe is longer, we have a larger pressure drop in the pipe, and if the pipe has a larger diameter with respect to a given size, then we have a smaller pressure drop in the pipe. And in most homes, what you notice is your cold water is a 3/4 inch diameter pipe, where the hot water is 1/2 inch. And that's because we use cold water more than we do hot water. So take another example. This would be the service entrance on a house, and sitting at the pole here we have a transformer, and this is alternating current, but right now it doesn't matter, same principles apply. And the feeder voltage should be 121 plus or minus 2 volts. Now, I'm only showing 2 leads coming in here. The black lead is actually the support lead. Usually there's 3 leads, including the support, for 240 volts, but in this case I'm not being concerned with that. And the house is drawing some current, don't know what, but the voltage drop in the service line is producing a voltage at the output of 118 volts. And what we can see from that, again, is we have a 4-volt drop in the wire for the service entrance. Now, if you have a furnace or perhaps an electric water tank, you may note when it turns on is you'll see your lights take a dip. And the reason is the starting surge current of the motor or the water tank's heater element causes a voltage drop in not only the service entrance, but all the wires leading from the transformer, I could theoretically say back to the power plant, through your fuse or circuit breaker panel, through your house wiring and so forth. Voltage drop, lights dip, the motor starts up, current drop, the current through the motor is reduced, and then the voltage drop in your house basically is returned somewhat to normal. So we can see that we lose voltage in this case, which would be 4 volts. Now, what happens with this voltage drop? I mean, we know we're taking energy to move an electron. We have to move it from the valence band into the conduction band, and even if it's a metal where the conduction and valence bands overlap, we still have to move the mass of an electron, which is 1/1800th that of a proton, and it takes energy to do that. Well, in our particular case here, that energy is in the form of heat. Now, if we take a look and apply Ohm's law very quickly here, and we're going to get into the details later, so don't be concerned about it, is we have a 4-volt drop in the service wire, and suppose our house is drawing 40 amperes. Power is equal to the product of voltage and current, and that turns out to be 160 watts lost in the service line. 160 watts, depending on the size of it, can be awfully, awfully hot. And if spread out over a large area, not so much. To give you an idea on that, on a perfect day with the sun directly overhead, the energy is 1,000 watts per square meter. So we have 160 watts basically heating up the wire coming into our house, and fortunately it's before the meter, so we don't have to pay for that. If we're after the meter, we would have to pay for it. So that's kind of a good thing. If the electric grid is overloaded, that is, say, in the summertime and everybody comes home and turns on their air conditioners, the actual feeder voltage of the grid can drop. And if it drops too far, that's referred to as a brownout. And the problem with that is that a lot of motors may not start. If they have starter windings, there's coils and or capacitors in it that allow for that motor to get started, and then a centrifugal switch kicks those starting components out and the motor runs. If it never gets to that speed or drops back down, the starter winding or capacitor will be clicking in and out of the circuit, and motor failure, given that happened long enough, will be imminent. So brownouts are kind of bad, and we hear about roving brownouts or blackouts in, say, California, and that's to deal with this, so we can avoid brownouts. Energy and power. Well, what's the difference here? Energy, and the symbol is E, and we have to be careful with this because in some circuits, E can be also used as voltage. So this is energy, and the unit we're going to be introducing here is the joule, and it's pronounced joule, and the symbol on that is a J. And to put this into perspective, 1 joule equals 1 watt of dissipated power for a time period of 1 second. Now, when we work into this, you're going to be seeing a lot of math and some confusing things, and not to be worried about that, but what to pay attention to is what happens to the units on this, because that's a very, very unique way of calculating problems and making sure you have the right conversion factor. So the symbol for power is P, and the unit is watt, symbol is W, time is T, the unit is seconds, and it's a symbol's lower case s. Uppercase S is conductance, which stands for Siemens. We'll talk about that later, but seconds is a lowercase s. Power, we'll get into this in more detail later, is equal to the product of the voltage times the current, or the voltage squared divided by the resistance, or the current squared times the resistance. And this could be, say, the resistance of a wire, the filament of a light bulb, or whatever. So power can be represent many different things. One would be heat, baseboard heater. Another, a light bulb, of course. Mechanical energy, suppose we have a furnace blower motor where 746 watts of power would be defined as 1 horsepower. So we're converting electrical energy into mechanical energy. And we have a lot of other things we can do with this too, pneumatic power and so forth. And let me just mention, in the case of a light, an incandescent light, for example, say 100 watts, you pay for 100 watts, and about 5 of those watts are actually converted to light, and 95 watts are heat. And that's why you probably, with your bare hand, cannot unscrew a 100-watt light bulb that's been on for a while. and that has to do with the inefficiencies, if you will, of an incandescent light versus say a light emitting diode or a CFL. So energy is equal to power times time. So if we have 5 watts dissipated for 1 minute, and say we're producing heat, how much energy is converted? So we're converting energy, electrical energy coming into our house, we'll say, to heat. And all we have to do is multiply this out, but what we have here is to convert the 1 minute into seconds. So we'll be doing this in detail later, but that would amount to 300 joules of energy. So it's just power times time for energy. Now, let's take a look at our electric meter on our house. And perhaps this will give us a better insight into what's going on. And you don't need to study this, just follow along the reasoning behind it here. We're going to start out at 10 a.m. and we're going to say the current number on the electric meter is 0. So that's going to remain 0 until 10 a.m. At 10 a.m. I'm going to turn on a 500 watt toaster. I'm going to leave it on for a half hour. I'm making a lot of toast. So what that meter will do is it will start to rotate, and little dials on it are also going around, and it'll increase, it'll ramp up to the point where I turn the toaster off. Now note that it doesn't go back to 0, and that's because we have used that energy and the electric company wants to be paid for it. Now let us suppose that I do nothing till 11 a.m. and then say I turn on a 1,000 watt baseboard heater to heat up a bedroom or something. Again, this will ramp up. This is going to be on for 1 hour. Now the total power, and actually this should be in kilowatt hours, it's an energy, will now sit at 1.5 kilowatt hours. And since the baseboard heater went off at that point, again, this remains flat. So the electric company wants to be paid for this usage and this usage. Now, what I use the energy for is up to me. The electric company doesn't care. All they want to do is get their money for the electrical energy coming into your house. So how do we find out the total amount of energy in this? And just pay attention to the units work on this. So we're going to start with the toaster here. 500 watts times 30 minutes. And what we know is we're going to have to convert this into seconds, equals 500 watts times 30 minutes times 60 seconds per minute. Now note the units on this. The minutes divide out and the seconds remain. So that is an easy way when you do conversions to make sure that you don't have this reversed, is to make sure that the units are right. And multiplying that out here, we had 500 times 1800 seconds, gives us an energy of 900,000 joules, or 900 e to the third power joules, or more preferably 900 kilojoules. So how much energy is used here in total? Well, now we have two things to calculate. First, our 500 watt heater for 30 minutes, and the second would be the 1,000 watt, this is our toaster rather, our 1,000 watt heater for 1 hour. So I'm just going to write this down here as 900 kilojoules because we just calculated. Now let's go through and figure out what this guy is. So I have 1,000 watts, and I'm using this for 1 hour, and I'm going to start by converting this into minutes. So I'm going to multiply that by 60 minutes divided by 1 hour. Notice that the units of hours drops out. So I'm down to minutes. Again, taking this and adding it to this guy, so we have 1,000 watts times 60 minutes. Have to get that down into seconds. So I'm going to multiply that by 60 minutes times 60 seconds per minute. Notice that the units of minutes drop out. And then what I get here is 1,000 watts times 3,600 seconds. Gives us 3.36 megajoules. And remember that mega is times 10 to the 6th power. So now to find out the total energy, all I have to do is add these guys together, and that comes out to be 4.26 megajoules. So an easier way to do this without doing the two steps, and I'll do it later, is to just figure out how many seconds are in an hour. And that's going to be 3,600. So you can do the conversion between hours and seconds very easily with only one term. So we're going to use this number later. So hopefully what you kind of understand here is the relationship between unity and power, 500 watts of power, 1,000 watts of power for this guy, and the energy that's being converted by the use of power over time. So joules, what good are they? They obviously measure energy use in a house. It is equal to 1 watt times a second, and it's wrong to say 1 watt per second. It's times 1 second. Now, if we want to measure energy in a house, this leads to a very large number, and we could see before we're talking about megajoules. So what the industry has done here is they measure energy for commercial and residential in kilowatt hours. Now, the thing to note here in kilowatt hours is that kilowatt is the power. It simply equals to 1,000 watts, and the time here is in hours, not in seconds. So kilowatt hour is in fact a measure of energy because it's made up of power times the time. So in steps, let's figure out how many joules are in 1 kilowatt. So I'm going to break this down here and worry about the kilowatts first. I have 1 kilowatt times 1,000 watts per 1 kilowatt. Now when I come up with these guys, I don't have these memorized. I think about the units. I know my answer has to be in watts. I know I have to get rid of kilowatts. That's how I assign these. Because I remember none of this stuff. It's just not important for me to remember it. I can figure it out on the fly that fast. So our 1 kilowatt equals 1,000 watts, which is pretty straightforward. Now we're going to take the time, and as we did before, we're converting 1 hour into 60 minutes, and here converting 60 minutes into 3,600 seconds by this would be getting rid of the hours unit, and this would be getting rid of the minutes unit, and the seconds here survive. Or I can do it directly, as I alluded to before. 1 hour times 3,600 seconds per hour gives us 3,600 seconds, and again the units of hours divide out. So what my 1 kilowatt equals as far as joules is concerned is 3.6 megajoules. Now kilowatt hour is a fairly friendly term to work with. I mean, number 1 subscripted by kilowatt hours as opposed to 3.6 mega. That is why kilowatt hours is a much better way of expressing larger amounts of energy. While I'm on this page, we can also go backward. The amount of energy needed to move an electron, say from the valence band in the conduction band, can also be measured in joules, except that number is extremely small. So there's another transformation into the electron volt. And that's a measure of energy also, but instead of ending up with a very small amount of joules, we talk about electron volts in reasonable numbers like we do kilowatt hours. Okay, getting down to the bucks here, at 13 cents per kilowatt hour, and that's fairly reasonable. Your bill is broken down into two things. One is a delivery charge to people that maintain the poles and the transformers and so forth, and the cost of electrical energy, which you can buy from Niagara Falls or whatever, any place you want. What does this previous example cost? How much is it going to cost us to run that toaster and the baseboard heater? So the energy we used was 4.26 megajoules, and what we have to do is convert that to kilowatt hours, and since we know the rate per kilowatt hour, calculating the cost would be straightforward. So first we need to know how many kilowatt hours we used, and I'm going to do this by breaking this down into the joules first. 4.26 was the result of our calculations on the previous page in megajoules, 3.6 megajoules per kilowatt hour. So this is what the equation looks like. And what is probably of concern is a compound division problem. But we'll figure that out in a second. It's really easy. So if I do the math on this, as we can see, we have a larger number divided by a smaller number. So my mental checksum on this is I know the answer has to be greater than 1. And it is. It's 1.183, repeat forever, kilowatt hours. The result of that whole thing. Now, how much does it cost? Well, this is the amount we used in kilowatt hours, and it's 13 cents per kilowatt hour. And remember, I want the units to be in dollars. So when I arrange this equation here, I know the kilowatt hours has to be in the denominator so they can divide out. And in doing that, I end up on the calculator with 1.53.8 e to the negative 3. And then shifting around the decimal point a little bit on that is what we see is that cost 15.38 cents to use that much energy. So let's spend a little time decoding the units here, because this can be, pretty intimidating when we talk about fractions and so forth. So I'm starting out only worried about the units here, and I have megajoules in the numerator divided by megajoules per kilowatt hour in the denominator. And what I'm going to do is take this and multiply it by 1, which is kilowatt hours over megajoules divided by the same thing, kilowatt hours over megajoules. So as we see from the standpoint of units here, is this equals 1. And what happens then is when we multiply the denominator, you can see that the kilowatt hours, oops, got an H there, divide out, and so do the megajoules. So we're ending up with 1 in the denominator of our complex fraction. So now what we have is megajoules times kilowatt hours per megajoule, and again dividing out the megajoules gives us an answer in kilowatt hours. So if you think about the way this works, especially this multiplication here, to simplify that fraction, it breaks it down into a manageable term that you can work with without having to be concerned about that big old guy. Because, you have another fraction in the numerator here. It really look confusing. But if we follow the rules and basically work with the units, remembering that we always have to end up with the right unit, things aren't so bad. How much energy is in a 12-volt, 60-ampere-hour car battery? Well, the published rating on the battery that I'm, going to buy is 60 ampere hours. And from the standpoint of energy, this infers that the operating voltage is 12 volts. Because 12 volts times 60 amps is going to be the power that we need when we do an energy calculation. So this is kind of inferred, and actually 12 volts isn't exactly correct because a car battery is a nominal 2.2 volts per cell. So it's really 13.5, sometimes 14 in the range of whether it's being charged or not, but we're just going to use 12 here. So we know that the energy equals power times time, and power equals voltage times current, and that's Ohm's law. We'll be seeing a lot more of that coming up. So what we end up with here is a total of 720 watts. So if I were to, say, put a resistance across that battery that drew 60 amperes, 12 volts, that would be dissipating 720 watts, which is a fair amount of power, depending upon the size again. So the energy in kilowatts then would be, moving the decimal point over 3 places to go from watts to kilowatts, would be 0.72 kilowatts. And if this is going to be run for 1 hour, the energy would be 0.72 kilowatt hours. And if we wanted to convert that into joules, we would have 2,592 kilojoules. Now, what's the danger when you work around electricity? Now, you're not going to get electrocuted by 12 volts, I suppose, unless you cut your chest open and stick a couple wires across your heart. But the dangerous part is the short circuit current. Now this battery is rated at 60 ampere hours, but in a short circuit condition this can be 1,000 amperes. And that can produce an awful lot of heat in a very, very short period of time, which is, well, very dangerous. So when you're working on car batteries, always take off the grounded terminal first, which in cars is a negative battery. Reason? You're taking the nut off, and that open-end wrench, will say, hits the frame of the car, nothing happens because they're at the same voltage. On the other hand, if you're taking the positive off first, and it hits the frame of the car as you move the wrench around, you've got short circuit across very, very energetic power source. Even if the battery is partially discharged, it can really hurt you. So you take the negative terminal off first, and you put the negative terminal on last. It's the safest way to deal with a car battery. It's not the voltage, it's the energy storage capability, which is dangerous. The other things that are kind of dangerous in a house is a microwave oven. And that has parts in it that can kill you, even though they're unplugged. So you have to be very careful. I don't recommend playing around with them. Okay, resistance yet again. Symbol's a squiggly line here. The unit is the ohm, after a physicist. And the symbol is the Greek omega symbol. And for an example here, I could say R is equal to 10 ohms. So in an electric circuit, which we'll be getting into in detail later, the voltage unit, V, and the unit's the volt, the symbol is V, and the current is I, and the unit is the ampere, and an ampere is defined as 1 coulomb passing by a given point in the circuit in 1 second. Now what's a coulomb? 6.24 e to the 18th electrons. So current flow is a rate. It's a rate of charge transfer in electrons per second past a given given point. Now let's look at some relationships here, and this is kind of the background for Ohm's law. But before we do that, let's take a look at the material tungsten. And suppose that I have a 60-watt light incandescent in a 100-watt incandescent light. Why is the power different? And the answer to that is in tungsten, and this is a metal that has the highest melting point, which kind of makes sense, is that the length and area are adjusted so that when 120 volts is applied, the current that flows in the case of a 60-watt light bulb would be half an ampere, and that'll dissipate 60 watts. Now in a 100-watt light bulb, either the filament is made a little bit, the area is increased a little bit, so more current flows, voltage remains the same, 120, hence the power goes up to 120 watts. So resistance can be embedded in things, is the point. It's embedded in wire, it's embedded in filaments, and it's also an explicit part. Here is a 10 ohm 5-watt resistor, a physical part that we would want to put in a circuit to do something. If we're using a surface mount part, I don't even know if you can see this, but that's a surface mount lead, and the corresponding resistor would be the same package size, which is called 1206 mils, would be about that large. And why would I need a resistor, which in this case is right there, it's 1/8 of a watt, is we'll see that a lead is nonlinear and something has to limit the current. So there's a need for a physical component that resists current flow. And the composition of that determines how much it resists current flow, and the size of it determines how much power it can dissipate. Like that little bitty resistor I pointed to, 1/8 watt, if I get over that, it's simply going to burn itself open. This guy, on the other hand, can get so hot I can't touch it and it'll operate fine. So let's take a look at the graph for all of this, and this looks a little bit busy here. I apologize for that, but it is what it is. And what we see here on the x-axis becomes our voltage axis. The arrows mean this extends to infinity, and then I have negative voltage here and positive voltage here. So before going on, let's kind of unpack that a little bit. In this particular example, we have current flowing this way, and this is the way I've drawn the batteries up to this point, or the cells. And if I reverse that, current flows in the other direction. So without getting into details on this here, is negative voltage simply means that relative to a common point, which is called ground, this is the third line coming into your house, the triplex, bare wire, this is the chassis of your car. Its common point is ground, is I can have voltage either positive or negative. Now, what Ohm's law says is that if I plot the current flow, I'm going to get a straight line which goes through the origin. What that means is without voltage you cannot have current flow. Think about it. Without water pressure you can't have water flow. In the case of this is a relatively gentle slope, is that represents a higher value of resistance. And in the dotted line here would represent a lower value of resistance. Because for a given voltage, as you can kind of see, the current in the first case would be here, current in the second case would be here. Speaking about current, that's going to be on the y-axis as the current. Again, arrowhead, positive I, negative I. The negative I would correspond with a negative V for one of these circuits. I haven't defined that yet. There's a reason I haven't. So that's kind of what Ohm's law looks like, and what's very important here is you see that it's linear. So since it is linear, I can say that any V, any voltage, divided by its corresponding current, that's this point on the graph, if you will, is going to be a constant. So we could also say that V1 divided by I1 is going to be equal to V2 divided by I2, which is going to be equal to V2 minus V1 divided by the corresponding I2 minus I1, which, guess what, is equal to V1 minus V2 divided by the corresponding I1 minus I2. And I can also have voltages over here in quadrant 3. Doesn't matter. So all of this points out is that Ohm's law is a linear function, and this is the guy that will tell you whether or not it's true. If you pick two different values of voltage and their corresponding currents, and they're not the same, Ohm's law does not apply. And this is in the static resistance sense. There's another type of application of Ohm's law which is called dynamic resistance. I'm not even going to discuss that here because that's a topic for a later study. So that's kind of important, and the thing to note here is that the slope of the resistance here, if it's steeper, means that the resistance is lower, and also that all of the lines here have to go through the origin. 0 volts equals 0 current. Now we could decompose this a little bit further, but it wouldn't be productive at this time to do it. So we talked about Ohm's law, and we said it's very linear. Let's talk about a device that isn't linear so we can contrast it. And that would be a light-emitting diode, and the symbol for that would be this. There's a little arrow coming off of it, and that arrow indicates that it's emitting light. So that's the symbol for a light-emitting diode. And its characteristic curve, and again we're using the same coordinates that we used in the other problem, is we see once we come off of zero here, and 0 voltage equals 0 current, is we start up a curve, and by curve means it's nonlinear. Now this is governed by certain equations, and basically what this means is that the operational point of this is what we say when we do circuit calculations for a green LED is about 2.2 volts. Now the same is true with red and yellow. Infrared can be 1.4 and 2.2. Why do we need infrared? We can't see it. Well, remote control television, infrared. And the different guy is blue and white. Now, white LEDs, not in a sign, in a flashlight, are blue or violet emitters that are doped with yellow emitting phosphor. So the core of that, the engine under the hood, is a blue LED. And blue is a higher frequency of light, which means it's more energy. So its value would be out here somewhere between 3.3 and 3.9 volts. Hence, if you have a LED Christmas tree string, the lights you look for, if your string is out, first are the blue lights. Because the current is constant, the voltage drop across blue is higher, they actually run hotter than the other color of light strings. Okay, anyway, so that's an example of a nonlinear device. And note that if we make V negative, is we have this leakage current which are flowing backwards. So if the current flow, I'm not going to draw it because there's two kind of current flows here, is flowing with the arrow, it'll emit light. If it's trying to flow backward through this, there'll be a little bit of leakage, but it will not light. Until you get over to here somewhere, where you break the thing down. And it just basically arcs, if you will, through the gallium and arsenide that thing is made from. Okay, so that's an example where Ohm's law would not apply, and let's move on to another concept here. Suppose I have a table, and I measure that from the floor and find it to be 3 feet high. Okay, and suppose I take my ruler and come off the ceiling and find the tabletop to be 5 feet low. Well, which defines where the tabletop is located? And the answer is both. Now we always would think about measuring from the floor and not the ceiling. But there's nothing wrong with measuring from the ceiling. Both exactly define where the tabletop is. So it is with electricity. We have resistance that we defined as how hard it is for current to flow, and we have another thought. Conductance is how easy is it for current to flow. Now, conductance may seem a little bit strange because with what we've built up so far with resistance, you can kind of see, pushing electrons from valence into conduction bands and so forth. But this is very, very useful. And the relationship is the conductance G is simply equal to the reciprocal of R. And contrarily, R is equal to the reciprocal of G. So, they're kind of friendly from the standpoint of equations. Now, where this comes in handy, and we're not getting into details here, is if I have two resistors in series, the total resistance is going to be equal to the sum of the two of them. And that kind of makes sense. I've got a 3/4 inch pipe connected to a 1/2 inch pipe. What's the total resistance? Well, it's the flow of water. It's the sum of the two of them. Now, if I have them in parallel, right next to each other, and this is the way your house wiring lights are in parallel, is I can say that, and I'm calling these RA and RB so as not to confuse these with R1 and R2, is each one of these will be conducting a current. And if we wanted to find out what that could be, we could say, well, what's the conductance of A, and what's the conductance of B? And then the total conductance would simply be the sum of the two. If I want to convert that into the total resistance, I just take the reciprocal of it. Now you might say, why do I want to do this? And that's a real good question, because we have simplified formulas for doing this directly with resistance that we'll be using. This is to make you aware of conductance because it comes in handy sometimes. If I had 4 resistors here, say, the formula I use, which I'm not going to write down, basically... Alright, it's me again. I'm back. 30-minute time limit on the filming there for the camera. What I was saying is that if we had, say, 4 resistors in parallel, and we'd be solving those using the R subscripts for resistors, probably not be using the conductance at all, but what sits inside of that formula, which we'll be learning about later, is inherent conversions into conductance. Then we do the adding, and then we convert it back into resistance. Conductance is also very, very helpful at high frequency for analyzing high frequency circuits. So with that I'll conclude, and thank you for watching.